Welcome to the key course Image Processing and Computer Graphics. My name is Matthias Teschner. I am professor for computer graphics at the University of Freiburg, and I organize this course together with my colleague Professor Thomas Brox, who is head of the image processing group at the University of Freiburg. The synthesis and the analysis of images are closely related to each other. That's why this course introduces concepts from both areas, computer graphics and image processing. I am the contact person for computer graphics. Professor Brox is the contact person for image processing. Please note that both parts, graphics and image processing, have separate web pages. In the following, I'm going to introduce the graphics part of the key course. The main topic in graphics is certainly the synthesis or the generation of images, also referred to as rendering. However, graphics is not only limited to rendering. Instead, graphics addresses topics that are related to rendering, namely modeling and simulation. In the context of modeling, graphics is concerned with the question how to represent scenes that we would like to render, and in the context of simulation, graphics is concerned with simulating or animating objects or materials over time, which is relevant for the rendering of dynamic scenes. So in this key course, we mainly look into rendering concepts, but we also address some modeling and some simulation aspects. This image nicely illustrates the three areas. So for instance, modeling is concerned with the question how to represent the geometry of the objects in the scene and also how to represent the reflection properties of surfaces in the scene. The rendering process is concerned with the computation of the light transport in a scene in order to finally generate the image, and simulation would be concerned with the dynamics in a scene, for instance with the simulation of a fluid. Here we have another illustration of the three areas. Modeling is concerned with the accurate and efficient representation of the geometry and the reflection properties of objects in the scene. Rendering is concerned with the computation of the light transport, and simulation is concerned with the dynamics in the scene, for instance elastic curtains or breaking glass. These images are also a nice illustration of an important motivation for using computer graphics concepts. Once you have a digital representation of a scene, you can render a scene for different settings. So for instance, it's rather easy to change objects in a scene, or you can remove or add objects in a scene. You can change reflection properties of elements in a scene, or you can change the illumination setting in a scene. For instance, you could render this room in the morning, or you could render this room in the evening. Here we have another example from the area of engineering. In this scenario, oil is simulated inside a gearbox. And again, all three aspects play an important role. In terms of modeling, the oil has to be represented, the geometry and the reflection properties of the gears and the gearbox have to be represented, and then the oil has to be simulated, and finally the images have to be rendered. This video illustrates some of the aspects that are relevant in the generation of the final sequence. So first of all, the geometries of the objects have to be specified. So here the gears and the gearbox are placed in the scene, and the surfaces of all objects are represented with triangulated meshes. Also, the reflection properties of all objects are specified. Here, for instance, some objects are opaque, other objects are transparent. The oil in this scenario is simulated with particles. So in the simulation, we compute the positions and velocities of all the oil particles over time. But in terms of rendering, we do not render the particles. Instead, we first reconstruct the isosurface between oil and air. And this isosurface is represented with a triangulated mesh. You can also specify reflection properties for this triangulated mesh, and then you finally compute the light transport in the scene to get the final image. Computer graphics concepts play an important role in a variety of application areas. And in the previous slides, we have already seen three examples. Computer graphics concepts are of course used for visual effects in movies, and they are also highly popular in commercials. Graphics concepts are used in architecture and also in engineering. In addition to rendering, graphics concepts are also used for visualization purposes. Here, medical imaging and scientific visualization are two example areas. And then there exist other application areas where efficiency plays an important role, for instance, games and virtual or augmented reality. Computer graphics is concerned with all aspects that are related to the generation of images. And this starts with the modeling of light. So in graphics, light is typically modeled with a set of small particles, also referred to as photons. These photons move along straight lines at infinite speed. Photons are generated by light sources and they are absorbed or measured by sensors. So for instance, if we take a camera, then photons hit the image sensor of the camera, and photons per time that hit a small area of the image sensor are interpreted as an intensity. Photons also interact at surfaces. So if a photon hits a surface, a photon can be reflected or it can be absorbed. This process is governed by the reflection properties of the surface. So for instance, if we have a dark surface, most incoming photons are absorbed. If we have a bright surface, most photons are reflected. The reflection direction also depends on the material of the surface. If we have a glossy material, then we have a different reflection pattern compared to the reflection pattern of a diffuse surface. Photons can also interact with material in air. For instance, if we have fog, then photons do not move along straight lines in between object surfaces, but they frequently change their direction. Now, modeling is concerned with all aspects that influence the light transport in a scene. So light sources and their properties have to be specified. The geometry of all objects in a scene has to be specified, and also the reflection properties of all surfaces. Now, rendering concepts are concerned with the computation of the light transport. So we have a description of the geometry and the materials of all objects in a scene. We have information about sources and the image sensor, and we know how light interacts at surfaces and with participating media. And using all this information, all rendering approaches try to reconstruct the light transport. In particular, the light transport towards the sensor, which represents the final image. The last aspect would be simulation. So here graphics approaches are concerned with the simulation of different materials. For instance, graphics research is interested in the simulation of rigid bodies, elastic objects, or fluids. Graphics research also addresses the interface between rendering and simulation. So for instance, if you have a particle-based fluid simulation, then there is a question how to render this particle representation. So once more, this slide illustrates the three areas: modeling, rendering, and simulation. Graphics is concerned with the representation of the geometry and the reflection properties of objects. Graphics is concerned with the simulation of materials, for instance fluids, and graphics is concerned with the computation of the light transport in a scene in order to compute photorealistic images. That's it about the introduction to the graphics part of the key course. In the following, I'm going to talk about organizational aspects. Then I will describe the research of the graphics group. After that, I'd like to introduce some aspects that are relevant for the generation of images, and finally I will introduce the course topics. But first of all, I talk about organizational aspects. This slide summarizes our teaching activities. First of all, we offer this key course where we talk about selected aspects of modeling, rendering, and simulation, with a main focus on rendering. In addition to the key course, we offer two specialization courses. One specialization course is concerned with rendering, the other one focuses on simulation. In the advanced computer graphics course, we look into so-called global illumination approaches, for instance radiosity or stochastic ray tracing. In order to realize photorealistic images, it is important to capture the entire light transport in a scene. So surfaces are not only illuminated by light sources, but surfaces also illuminate each other. And such effects are captured by global illumination approaches such as radiosity or stochastic ray tracing. And in the advanced computer graphics course, we focus on such global illumination approaches. In the simulation course, we are concerned with concepts to simulate deformable objects, rigid solids, or fluids, and in this context we mainly look into particle-based approaches. In addition to the 3 courses, we also offer seminars, an animation seminar and a rendering seminar, and we also offer all types of projects and theses. We offer bachelor projects, master projects, lab courses, bachelor and master theses. In terms of the projects and the thesis, we distinguish 2 tracks, a simulation track and a rendering track. When interested in graphics at the University of Freiburg, you can either focus on simulation or on rendering. So if you are more interested in simulation, you can start with the simulation course in the winter term. In the following summer term, you could attend the key course on graphics. The key course and the simulation course are rather independent. The key course has a strong focus on rendering, so it is not necessarily a prerequisite for the simulation course. In the summer term, you could also do your lab course or attend the simulation seminar. Then in the following semester, you could continue with the master project and then finally write your master thesis. In the rendering track, you would start with the key course in the summer term, and then you could attend the advanced rendering course in the following winter term. In parallel, you could also participate in a lab course and in a master project. Of course, you could also attend the rendering and the simulation seminars. Again, the track would be completed with the master thesis. I find it particularly important to thoroughly plan the projects and the thesis. On one hand, one could do the lab course, the master project and the master thesis in different areas of computer science. The question, however, is whether this makes sense. I would actually argue that it is better to do the lab course, the master project and the master thesis in the same area. In this case, the master thesis can be built upon the results of previous projects. This is illustrated here for both tracks. In the simulation track, for instance, one could implement a simple fluid solver in the lab course. This simple fluid solver could be extended or improved in the master project. For instance, the data structures for the neighbor search could be improved, or the pressure computation could be improved by incorporating a so-called PPE solver, where PPE stands for pressure-Poisson equation. Based on the results of the master project, it would be possible to write a master thesis that addresses very interesting, challenging and relevant aspects in fluid simulation. So in the master thesis, it would be possible to focus on a research-oriented topic. The same holds for the rendering track. In the lab course, you could start with a simple ray tracer. In the master project, this ray tracer could be extended to a sophisticated stochastic ray tracer that employs Monte Carlo integration, and the data structures for the ray traversal could be improved. Then the outcome of such a project can be the basis for a highly interesting rendering topic that is covered in the master thesis. So let's get back to the key course. In terms of the course material, all slide sets, all recordings and also the exercises and the solutions and a test exam can be found on our webpage. On our webpage there is a section about the key course, and within this section you find links to all these materials. At the end of the semester there will be a written exam about both parts of the key course, graphics and image processing. For the graphics part of the written exam, only the slide sets and the recordings are relevant. The exercises and the solutions to the exercises of the graphics part are not relevant for the exam. If you are interested in graphics, in particular in rendering concepts, I'd like to recommend these books in addition to the course material. I do not go into the details of all these books. I'd just like to point out that the first 2 books are available for free. So there's a free download of Principles in Digital Image Synthesis available, and there's a free online version of the book Physically Based Rendering from Theory to Implementation. In addition to the lectures, we also offer exercises. These exercises basically implement an introduction to OpenGL, which is a programming interface for rendering. So we have planned 4 exercises. Each of these exercises consists of 2 tasks. Each of these exercises addresses 2 topics. And the topics of the exercises are related to rasterization, homogeneous notation, projection, and Phong shading, which are of course topics of the lectures. For support, you can contact a student assistant. And it's also interesting to note that the exercises are optional. So the exercises are not relevant for the written exam. In terms of prerequisites, it's recommended that you have some basic knowledge in linear algebra and calculus. For instance, you should know how to multiply a matrix with a vector, you should know the inverse of a matrix or the transpose of a matrix. In terms of calculus, you should have some basic knowledge in differentiation and integration, and for the exercises it might be relevant to have some basic knowledge of a programming language such as C or C++. That's it about the organization of the key course. Now in the following I'd like to talk about the research of our group. Our research focuses on simulation, and this video illustrates some aspects of this research. So here we see a particle simulation. In this example, all objects and substances are represented with particles. For instance, the entire fluid volume is sampled with particles, and also the canyon and the creatures are sampled with particles. Now, the main task in a particle simulation is the computation of particle positions over time. Therefore, we consider forces at the particles. These forces change the velocities of the particles, and the velocities change the positions of the particles. In terms of forces, we compute forces that depend on the respective material of a particle. So, for instance, for rigid particles, we compute contact forces. At fluid particles, we compute compression forces and viscosity forces. At elastic particles, we compute compression and shear forces. In terms of rendering, we typically avoid the rendering of individual particles. Instead, we typically render surfaces. For instance, for the fluid, we render the interface between fluid and air. Sometimes we explicitly reconstruct and render a triangulated representation of this interface. In other cases, we work with an implicit representation of the interface and do not have an explicit representation. In our research, we focus on efficiency and accuracy. So in this scenario, we have millions of particles, but we can also process billions of particles in other scenarios. And in terms of application areas, we do not only address animation, but we also have applications in engineering and other areas. Particle simulations are also referred to as Lagrangian simulations, and in this slide I'd like to outline the setup and also indicate the problem that we solve in Lagrangian simulations. First of all, we start with a volume of an object that we would like to simulate. This volume can either be a fluid, an elastic solid, or a rigid body. So any type of material can be simulated with particle-based approaches. The volume is subdivided into particles. So each of these particles represents a small portion of the original volume of the material that we simulate. Each of these particles has some volume and mass, and it is characterized by the density of the material. Each particle is further characterized by a representative position and velocity. And in the initialization process, the positions and velocities of all particles are defined. And then the task of a simulation is actually to compute the position x of a particle I over time t, and also the velocity v of a particle I over time t for all particles. And therefore we compute forces at the particles. These forces change the particle velocities, and the velocities change the positions of the particles. That's the concept of a particle-based simulation. And again, in terms of forces, we consider forces that depend on the material. So dependent on whether we have a fluid particle or an elastic particle, we apply the respective forces. This image illustrates a typical particle representation that is used in a particle simulation. Blue particles represent a fluid, where the saturation indicates the velocity of a particle. Blue particles are slow, while white particles have a larger velocity. Brown particles and yellow particles represent rigid objects. So it's interesting to note that particles can represent arbitrary types of material, and particles are particularly appropriate to represent complex geometries, as can be seen for the ship. Please note that particles do not have a spherical shape. In general, we do not know the shape of a particle. We know the size of the volume, but we do not know the exact shape of a particle. Only for visualization purposes, it's popular to render spheres, but particles are not spheres. In this slide, I'd like to discuss aspects that are relevant for the computation of particle movements. So in general, our task is to compute positions and velocities for all particles over time. We always start with a known position x and a known velocity v for some particle I at some time t, and our task is to compute the unknown position x and the unknown velocity v for particle I at time t plus delta t, where delta t is a small time difference, also referred to as time step. For the computation, we consider two governing equations. We consider one governing equation for the velocity as indicated here, and a second governing equation for the position. The governing equation for the velocity states that the time rate of change of the velocity corresponds to the accelerations at a particle. Here we have stated three accelerations that we typically use for fluid particles. We have the pressure acceleration, we have the viscosity, and the gravity. This equation is also referred to as Navier-Stokes equation. The second governing equation states that the time rate of change of the position corresponds to the velocity of a particle. In addition to these two governing equations for the velocity and the position, we also consider a constraint for the velocity. This constraint states that the divergence of the velocity field should always be zero. The divergence of the velocity corresponds to the time rate of change of the density, so if the divergence of the velocity field is zero, then this corresponds to the fact that the density of the fluid does not change, which means that we end up with an incompressible fluid. And the fact that the time rate of change of the density is related to the divergence of the velocity is also referred to as continuity equation. In order to compute velocity changes at particles, we need to compute accelerations. And the computation of these accelerations typically involves the computation of spatial derivatives. So for instance, for the pressure acceleration, we need to be able to compute the gradient of the pressure P. And therefore we use so-called discretization schemes. Here, smoothed particle hydrodynamics, or SPH, is one of the concepts that can be used, and this is indicated here on this slide. So for instance, the gradient of the pressure P of particle I at time t can be approximated by computing a sum over adjacent particles j. So j refers to all particles that are close to particle I. We also say that particle j is a neighbor of particle I. So by computing sums over the neighbors of particle I, we can approximately compute a spatial derivative, for instance, the gradient of the pressure. The same idea can be used for other derivatives, for instance, for the Laplacian of the velocity. Once we have all the accelerations, then we can update the velocity with a numerical integration scheme, and finally we can update the position with a numerical integration scheme. Here you can either use simple schemes, such as explicit Euler, or you can take any of the Runge-Kutta variants, or you can take Verlet. In the previous slide, I've outlined the concept that we use in particle simulations. Now here I'd like to explain some aspects of the implementation of a particle solver. And in this example, we look into a particle solver that simulates a fluid, and we look into all steps of one simulation step of such a solver. So we start with the particle representation of a fluid, and for all particles we search neighbors. So in this illustration we have a particle I, and we search all neighbors j of this particle within a certain distance. The neighbors of a particle are required to compute sums over these adjacent neighbors. And these sums approximate, for instance, accelerations at a particle. In the next step, we compute the predicted velocity v star at the next time step. So v star refers to a prediction of the velocity at the next time step, and here we apply accelerations at a particle. So in this case we apply the viscosity acceleration. The Laplacian in this case is implemented as a sum over adjacent particles, and we also apply gravity. We do not apply the pressure acceleration. The pressure acceleration is actually used to enforce the constraint that the velocity field should be divergence-free. So we remember, if the divergence of the velocity is 0, then the time rate of change of the density is 0, which corresponds to incompressibility. And incompressibility is an important property of realistic fluids. So in order to enforce the constraint and in order to compute pressure, we consider this equation at each particle. In this equation, V star is our predicted velocity and P is our unknown pressure. And this equation states that we would like to find pressure such that the divergence of the velocity change due to the pressure acceleration cancels the divergence of the predicted velocity. So we are interested in pressure such that the respective acceleration and the respective velocity change makes our velocity field divergence-free. In this equation, the gradient and the divergence operator are implemented as sums over adjacent particles. So we end up with a linear system with unknown pressure values P. Then we solve this system to get pressure values at all particles. In the final step, we apply the pressure acceleration to the predicted velocity in order to get a corrected velocity v for particle I at time t plus delta t, which is our final velocity at the next time step. And we also apply the velocity at time t plus delta t to advect the particles or to move the particles from the current position xt to the position xt plus delta t at the next time step. As you can imagine from this overview, the neighbor search and also the pressure computation can be particularly involved. As mentioned in the discussion of the previous slide, the neighbor search is typically a comparatively expensive task in a particle simulation. So it's an interesting research topic. Here in this scenario on the right-hand side, you can see a fluid simulation with up to 500 million fluid particles. So you can imagine that the neighbor search in such a setting is expensive. In a 3D simulation, we typically consider up to 40 neighbors per particle, and we typically have thousands of simulation steps. And the neighbors have to be re-estimated in each simulation step, as all particles move relative to each other in a fluid. We even have scenarios with billions of samples. So in this case, we have to identify about 40 billion neighbor particles per simulation step. In order to accelerate the search, we use acceleration data structures. And here we have a focus on uniform grids. Uniform grids are conceptually simple, but there exist a variety of possibilities to implement uniform grids. And here we have a focus on sorted lists and compact hashing. Another important aspect of our research is the optimization of so-called secondary data structures. When we use acceleration data structures, then we typically build additional data structures. So in each simulation step, we generate an additional data structure that we query to accelerate the search. And here our goal is to actually minimize these secondary data structures in terms of computation time and memory consumption. Another interesting aspect of our research is the pressure computation. So we remember that we consider the equation that is shown here on the right-hand side at each particle, and this equation is also referred to as pressure Poisson equation. The divergence and the gradient operators are implemented as sums over adjacent particles, and then we end up with a linear system as indicated here with unknown pressure values P. The system is sparse, but nevertheless the system is big. If we have 1 billion samples in a simulation, then we have 1 billion unknown pressure values in this system. And we have to solve this system in each simulation step. Here in this context, our research focuses on the implementation of solvers, and in particular we are interested in implementing matrix-free solvers. So we do not want to represent matrices or sparse matrices, and we are interested in parallelizable implementations. Our research focuses on efficiency and accuracy. Sometimes people think that simulations can either be accurate or efficient, but this is of course not true. So why should efficient simulations necessarily be inaccurate, or why should accurate simulations definitely be slow? And as we focus on both aspects, efficiency and accuracy, our research is actually applied in a variety of application areas. In the context of visual effects, for instance, we have collaborated with Pixar. In the context of engineering, we closely collaborate with 52. 52 is a company that has been founded by previous members of our group, and 52 develops simulation software with a main focus on the automotive industry. And then we also collaborate with an artist, and we have also collaborated with the DFKI in Bremen, where we have simulated underwater robots. Now I'd like to show two videos to illustrate the wide range of application areas of our research. Here in this first video, you see objects that are simulated as a highly viscous fluid. And the results of these simulations have been used by the artist Claudia Compt in her work. In this project, we also collaborated with 52. So we used PreonLab, which is the software that is being developed by 52, and we used PreonLab for pre- and post-processing of our simulations. Now here in this second video, we see an engineering example. This simulation has been performed by a customer of 52 using PreonLab. The scenario is referred to as water wading, and in such scenarios people are typically interested in finding out which parts of the car get wet, and they are interested in measuring pressure at surfaces. Compared to real experiments, simulations can have certain benefits. In terms of sensors, you can place arbitrary types of sensors at arbitrary positions in a simulation, which is much more flexible compared to real experiments. And also the evaluation of sensor values is more flexible and more efficient compared to real experiments. Another benefit is that if you are not happy with the simulation result, if you would like to change something, then it is of course easier to modify the virtual model instead of modifying or even rebuilding the actual car. That's it about our research, where we have a strong focus on simulation. Now we get back to rendering, which is the main focus of this key course. In the following, I'm going to discuss selected parts that are relevant for rendering or image generation, and I will also introduce the course topics. Here you can see some aspects that are relevant for a rendering setup. If you would like to render a scene, then you have to specify light sources and a light sensor, and you have to specify objects. These objects have geometries and the surfaces have reflection properties. You might want to consider participating media, or you might want to consider moving objects. In this case, you have to specify animations or perform simulations. And last but not least, you have to model the behavior of light. You have to have a notion of how light moves through space. You have to know how light interacts at surfaces or with participating media. All these aspects are relevant in a rendering setup. Based on our setup, we can now render an image. When we render an image, we typically accomplish two tasks. We find out what is visible at the sensor, and we compute color values that are measured at the sensor elements. By computing the color at a sensor element, we actually compute the light that is transported from a visible part of the scene onto the sensor. In terms of visibility, there exist two popular concepts. One idea is to project the entire scene onto the sensor plane. This is, for instance, employed in so-called rasterization approaches. The other idea is to trace rays into the scene and to estimate intersections of these rays with objects in the scene. Both concepts, projection or rasterization and ray tracing, will be explained in the key course. For the color computation, we actually use governing equations that model the light interaction at surfaces and within participating media. The so-called rendering equation governs the interaction of light at surfaces, and the volume rendering equation governs the interaction of light within participating media. Based on the materials of surfaces and based on the light source setting, the rendering equation describes which portion of the incoming light is reflected into which direction. So the rendering equation is evaluated to estimate how much light is transported from a visible surface onto the light sensor. So when we compute the color that is measured at a sensor element, then we actually compute the light transport from the scene onto this sensor element. In the key course, we use a simplified version of the rendering equation, which is referred to as Phong illumination model. In the advanced graphics course, we work with the full form of the rendering equation. And there we use stochastic ray tracing or radiosity to solve the equation. In the context of light transport computation, local refers to the fact that certain effects are ignored and that the setting is simplified. For instance, surfaces are not only illuminated by light sources, but also by other surfaces. And this is typically ignored in local approaches. In contrast, global approaches try to consider all relevant effects. They actually try to compute the entire light transport in a scene to eventually get a more accurate estimate of the light that is transported towards the camera or the viewer. Now we look into some more details of our light model. We already know that light is represented with photons, and these photons move along straight lines with infinite speed. In this context, infinite speed refers to the fact that we are typically not interested in the simulation of the movement of photons. Instead, we consider an equilibrium state. When we render an image, we are just interested in computing how much photons per time hit the small area of a sensor element. Light is emitted by light sources. At surfaces, light is scattered or absorbed, which is governed by the rendering equation. Light can also be absorbed or scattered within participating media, which is modeled by the volume rendering equation. And finally, light is absorbed or measured by a sensor, which can be a camera or a viewer. This slide illustrates these aspects. First of all, light moves along straight lines. At any point in space, there's light that moves in any direction. Light is generated at light sources, as indicated here in this illustration. Then light interacts at surfaces. Here we have two surfaces where the black arrow indicates some incoming light, while the gray arrows indicate reflected light. Now, based on the material properties, the reflection patterns are different. If you have dark material, less light is reflected. If you have bright material, more light is reflected. If you have a glossy surface, most light is reflected into a small range of directions. If you have matte material, light is equally scattered into the entire hemisphere. Light does not only interact with surfaces, but light also interacts with participating media. If light moves through fog, then fog scatters or absorbs some light. And these two types of interaction, the interaction with surfaces and with participating media, are governed by equations, namely the rendering equation and the volume rendering equation. Finally, we are interested in measuring how much light is absorbed by our sensor. This corresponds to the rendering of an image. Photons are characterized by a wavelength within the visible spectrum. This basically means that photons have a color. Here in this simplified illustration, we assume that photons can have three different colors. There can be red, corresponding to a wavelength of lambda 1. There can be green, corresponding to lambda 2. Or there can be blue with a wavelength of lambda 3. And now in light, these photons with three different colors can be mixed. If you have only red photons, then we have red light. If you have the same amount of red and green photons, but no blue photons, then we have yellow light. If you have the same amount of red, green and blue photons, then we have white light. So the distribution of wavelengths within the set of photons that characterize some light is interpreted as a color. So when we measure photons per time per sensor area, then we measure two aspects. We measure the intensity, roughly corresponding to the number of photons per time, and we also measure the color of the incoming set of photons that corresponds to the distribution of wavelengths within this set. Now in the following, I'd like to discuss the governing equations that describe how light interacts with surfaces and with participating media. The rendering equation describes how light interacts with surfaces, and the volume rendering equation models how light interacts with participating media. First, we look into the rendering equation, and then I'm going to discuss the volume rendering equation. Here we discuss the rendering equation. The rendering equation describes how much light is reflected into a particular direction given the amount of incoming light from all directions and also given the reflection properties of the surface. The setting is indicated here on the left-hand side. If you have a point P on a surface, we have incoming light L of P and omega I, which basically means that we have incoming light at point P from direction omega I. In 3D, omega I is a two-dimensional direction, and the goal is to compute the amount of reflected light into a direction omega O, here indicated with the gray arrow. And now the rendering equation states how to compute the reflected light from P into direction omega O using the incoming light at point P from all directions omega I. In the rendering equation we have L P omega I, which is the incoming light from direction omega I. This light is multiplied with the cosine of an angle theta, which is the angle between the surface normal at P and the incoming light direction omega I. This vector basically accounts for the strength of the illumination. So dependent on the direction of the incoming light, we have different strengths of illumination. Light that moves orthogonal to the surface has a stronger effect than light that moves more parallel to the surface. The integrand also contains a factor mat, which accounts for the reflection properties at point P. The term describes how much light from the incoming direction omega I is reflected into the outgoing direction omega O, so it basically describes the material. Now the term material times incoming light times cosine theta is integrated over the entire hemisphere, and we end up with the light that is reflected from point P into the direction omega O. And this integral equation is the so-called rendering equation, and it governs the interaction of light with surfaces. So in particular, based on incoming light and based on the material properties, we can compute outgoing light into a particular direction. In this key course, we always assume that light only interacts with surfaces and that light does not change when moving through space in between surfaces. However, light transport is actually affected when light moves through space and when there is participating media in that space. In such a case, light moves, for instance, through 2 points in space, P and P1, along direction omega. And now, when there is participating media, we can consider 4 effects that influence the light movement. 2 effects have positive contributions, while 2 effects have negative contributions. For instance, light can be absorbed between points P and P1 as indicated by the respective equation. Light can be emitted, so we can add some light while moving from P to P1, or we can have inscattering and outscattering effects. Outscattering means that light that originally moves along direction omega changes its direction into any other direction, and inscattering refers to the effect that light that has originally moved into another direction changes its path into the direction omega. The governing equations are very powerful. They can actually be used to compute the entire light transport in a scene. This is illustrated here for the case of a simple scenario where we have 2 cuboids in a box with a light source. And here we assume that we know everything. We know how much light is generated into which direction by the light source, and we also know the reflection properties of the surfaces. This means we know how much incoming light from any direction is reflected back into the scene in any direction. And now we could consider the rendering equation at each surface point for each outgoing direction, and then solve a system to simultaneously compute the reflected light from all points into all directions, which is actually a representation of the entire light transport in the scene. Actually, all rendering approaches are motivated by this concept. All rendering approaches approximately solve the light transport in the scene. Some approaches impose less simplifications, other approaches use more simplifications. If we know how much light is reflected from all points into any direction, then the rendering of a scene is just a simple lookup. We can place a sensor at an arbitrary position with an arbitrary orientation, and then we can consider viewing rays from the sensor into the scene as indicated here. So for a sensor element indicated by the yellow dot on the view plane, we can establish a viewing ray that is traced into the scene. For this viewing ray, we compute the first intersection with the scene, here indicated with the yellow dot at the blue triangle, and finally we look up the light that is reflected from the intersection point towards the sensor element. So if you have computed the entire light transport in a scene, then the rendering is a simple lookup. In practice, however, many approaches work the other way around. So typically start with a viewing ray. We trace the ray into the scene and we compute the intersection point with the scene. Then we compute the light that is reflected from the intersection point along the viewing ray towards the sensor. And in order to estimate this light, the rendering equation is solved at the intersection point. And in order to be able to evaluate the rendering equation, we need to compute the incoming light at the intersection point. And therefore we trace further rays from the intersection point into the scene to find out how much light is transported from other scene points to this intersection point in order to solve the rendering equation at the intersection point. So all rendering algorithms try to approximately solve the light transport in a scene. One approach that is very closely related to the concept that I've illustrated in the previous slides is radiosity. In radiosity, we actually compute reflected light at all surface points into all directions. This is typically a complex task, and the original radiosity formulation uses certain simplifications. For instance, there is no participating media in the scene, and the object material is restricted to diffuse or matte surfaces. This means that incoming light is uniformly reflected into all directions, which particularly means that the reflection of light is independent from the direction, which also means that we just have to compute one value for diffuse surfaces, namely the overall amount of reflected light. And from this overall amount of reflected light, the reflected light into one particular direction can be easily deduced. Another simplification is the discretization of surfaces. Instead of considering an infinite number of surface points, we just consider a finite number of finite size surface patches. So basically we consider a triangulated surface with n triangles, and then for each triangle we compute the reflected light into the scene. So in radiosity we solve a linear system with unknown reflected light per surface patch. The radiosity rendering concept will not be covered in this key course. Instead, it's covered in the advanced rendering course. Other popular rendering algorithms are, for instance, ray tracing and rasterization. So by either tracing a ray into the scene or by projecting the scene onto the sensor plane, these concepts actually compute visible surfaces. They solve the visibility problem. They find out which parts of the scene are visible at a sensor. These concepts are typically combined with so-called shading models. So rasterization is typically combined with the Phong illumination model to find out how much light is transported from a visible scene element towards the viewer and which color does it have. And ray tracing is typically extended to Monte Carlo ray tracing to approximately solve the rendering equation at an intersection point to compute the light transport back to the sensor. Ray tracing, rasterization, and the Phong illumination model will be covered in this key course. Monte Carlo ray tracing will be covered in the advanced graphics course. Here we have two illustrations for ray tracing and rasterization in order to show that both concepts actually solve the same problem. In both cases, we have a point P in our scene, and we would like to find out that this point is visible at position Q on a sensor plane. In ray tracing, shown on the left-hand side, we consider a ray. We trace a ray through point Q into the scene. We find the intersection point P, and then we know that P is visible at position Q on the sensor. In a rasterizer, shown on the right-hand side, we would perform a transformation of all scene points onto the sensor plane. In particular, we would transform point P onto the sensor plane, and point P would be transformed to position Q. So in both cases, in ray tracing and in rasterization, we find out that Q is the projected position of the scene point P. In terms of the transformation in the rasterization concept, we typically employ the homogeneous notation. This is indicated here with the 4x4 matrix, which would be the homogeneous matrix notation of a transformation in 3D. This concept, the homogeneous notation, will also be covered in the key course. In order to compute the light transport from a scene position P towards a sensor position Q, rasterization and ray tracing have to be combined with a shading model, and these shading models always base on the rendering equation, which is shown here once again. We remember that the integrand characterizes incoming light from a direction omega I, weighted with the material properties at point P, and that this term is integrated over the entire hemisphere. Now, ray tracing is typically combined with Monte Carlo integration, where the integral in the rendering equation is approximately solved at scene point P in order to compute the reflected light from point P into direction omega O towards the sensor position Q. Alternatively, rasterizers are typically combined with the Phong elimination model. The Phong elimination model bases on the rendering equation, but introduces more severe simplifications. For instance, in the integral of the rendering equation, the Phong model only considers incoming light from light sources. So typically, ray tracing is combined with Monte Carlo integration to approximately solve the rendering equation, which is a more accurate shading model. In contrast, rasterization is combined with Phong illumination, which is a less accurate shading model. Here in this last slide of this section, I'd like to discuss some aspects that are relevant for realistic images. Obviously, the most important aspect is the rendering concept. We always try to reconstruct the entire light transport in a scene as accurate as possible. If this is not possible, and in all practical concepts it is not possible, then it is important to understand the simplifications that we have introduced in order to minimize potential quality loss in the rendering process. In addition to rendering, modeling is also highly important. The geometry should be detailed, the specification of material properties should be detailed, and also the illumination setting should be as realistic as possible. If the geometry is unrealistically simple, if the reflection properties are unrealistic, or if the illumination setting is simplistic, for instance with just one point light source, then we cannot expect to get a realistic image, no matter how accurate the computation of the light transport would be. So all these aspects are important. So the rendering should be as good as possible, but also the modeling should be as good as possible. That's it about the introduction to rendering aspects. Now in the last part of the presentation, I'm going to summarize all the topics that will be covered in this key course. After this introduction, we start with ray tracing. We will see how to use ray tracing to find out which parts of a scene are visible at a sensor. In the next part, we look into shading, where we will see how to compute the amount of light that is reflected from a scene point towards the sensor. Here we particularly discuss the Phong illumination model. Then we introduce the homogeneous notation. The homogeneous notation is very popular in the context of transformations. When it comes to the representation of transformations, people often use the homogeneous notation because it is very elegant, versatile, and has certain benefits. The next topic will be projection. Here we will see how to solve the visibility problem by projecting a scene onto the sensor plane. And in this context, we will apply the homogeneous notation. The next topic is rasterization, where we talk about concepts for vertex and fragment processing. So let's assume you would like to render a triangle. Here the three corner points are referred to as vertices, and if the triangle is projected onto the image or sensor plane, then for each pixel position that is covered by the projected triangle, a fragment is generated. And then these fragments are processed. For instance, colors are computed for these fragments, and also the visibility is checked for these fragments. And in the context of rasterization, we talk about the so-called rendering pipeline, which combines vertex processing, rasterization, fragment processing, and also the Phong illumination model in order to generate images. Then, towards the end of this course, I will also introduce topics from modeling and simulation. In particular, I will briefly talk about curves, surfaces, and particle fluids. Then at the end, I'm going to summarize all relevant material and I will give an outlook. I will present a test exam that can also be found on our webpage, and I will also talk about radiosity, Monte Carlo ray tracing, and simulation aspects so that you can get an idea about the content of our advanced courses on rendering and simulation. So that's it about the introduction to the graphics part of the key course on graphics and image processing. In the beginning, I've introduced the three main areas of computer graphics: modeling, rendering, and simulation, and I've also discussed the practical relevance of graphics. Then I've talked about organizational aspects. I have introduced simulation aspects, which is the main focus of our research. I have introduced some rendering concepts for the generation of images, which is the main focus of this key course. And then at the end, I've summarized all the topics that will be covered in the key course. Thank you for your attention.